Greetings. Hi, I'm Kathy. I'm with the Friends of Arlington's David M. Brown Planetarium, and we are here tonight to talk. Oops. I'm sorry about that. Have a little glitch there. All right, let me start that over again. Greetings. Hi, I'm Kathy. I'm with the Friends of Arlington's David M. Brown Planetarium. We're here tonight to talk about the DART project. And Dr. Matthew Knight with the U.S. Naval Academy is going to tell us a little bit about what DART is and his involvement with it. And I'm going to go ahead and turn it right over to him and let him tell us. You can ask questions in the chat this evening, and go ahead and just stick them right in there, and we'll try to get them to Dr. Knight as we can. We can also have some time at the end for a little more Q&A. So with that, Dr. Knight, if you want to go ahead and share your screen with us.
All right. And are you seeing that full screen now?
Yes, we are.
All right. Well, thank you very much for having me. As Kathy said, my name is Matthew Knight. I'm an assistant professor at the U.S. Naval Academy in Annapolis, Maryland. And I've been involved with the DART mission for 5 years or so, since it was actually just a concept, yet not yet even selected by NASA. So I'll just be giving you an overview of the mission and talking somewhat about my involvement in it, or the primary things. I just want to start out by saying that this is a very large consortium of institutions and schools that are involved with it. It's obviously a NASA mission, but it's run by Johns Hopkins Applied Physics Lab in Columbia, Maryland. So very close to where I presume most of you are. So let me go ahead with this first video. It may not play so well, but I hope you all can kind of see it, and then I'll talk through what happens. But this is a video that's put together just to show you what the mission is all about. So we have a spacecraft, the DART spacecraft, which will intentionally crash into an asteroid, creating an impact which will move the asteroid very slightly in its orbit. And in doing so, it will be our first test of how we might defend the planet against a potential impactor. Here's a still frame, which will go over the same things I just mentioned, but you can kind of absorb each of these bits in a little bit more detail here. So the DART mission actually launched late last year, just before Thanksgiving, November 23rd, from Vandenberg Space Force Base in California. The DART spacecraft shown there on the left-hand side will be impacting an asteroid, and it's actually it's a system. The system is called Didymos and consists of a larger asteroid in the middle and a small asteroid that's a moon of that bigger one. And so DART will be impacting that moon, Dimorphos, on September 26th of this year, so just under 5 months. And by crashing into it, it's going to change the orbital period of the moon. So how long does that moon take to go around the main asteroid? And we're going to be able to observe that from the ground here on Earth and determine exactly what has changed, or learn about what has changed, and give feedback to NASA and to scientists of what we would do in the future if we had an impactor that was actually going to hit Earth. Because I want to stress that the Didymos system, Dimorphos and Didymos, are not going to hit Earth. They are never going to hit Earth. There is no hazard whatsoever from this, but we are just trying to learn on a safe system so that if we had something in the future we need to defend against, we're prepared to do so. So just to give you a little bit more background on this, on motivation for why we would have a mission like this. So Earth does get hit by space debris all the time, naturally occurring space debris all the time. You've probably seen a meteor in space, in the sky. You look up, you see a shooting star, so to speak. That's a little bit, a fragment of dust from a comet or an asteroid. And those small pieces are not problematic, but as the pieces get bigger and bigger, they can start to become a problem. So this plot here shows all reported what we call fireballs, so large meteors over the last about 30 years. And the size is roughly proportional to how big the object probably was. And you'll see one particularly big red dot, the worst or the largest impactor that we know of in the last about 30 years, that happened over Russia in 2013. If you have not ever seen a video of that, it's called Chelyabinsk. It's shown over there on the right-hand side, the top right. And it's pretty fascinating to watch that video. The impactor did not actually hit the ground. It exploded in the air, but it was a serious blast. People were injured. And it's some interesting videos to watch. So I'd encourage you to check that out if you're interested. Another way of thinking about possible impacts is to talk about the rate of impacts by different sized objects. So there's a lot going on this slide, but the real takeaways I want you to have are to think about that top row on sizes, and then if you look down at the fourth row there, the numbers of objects that we think that are out there that might potentially pose a problem over time. So at the small end on the far left are things that are a few meters in size. Those probably hit Earth about once a year, and there are probably hundreds of millions of those out in space. But at that size, they are not significant risks to Earth. As you get bigger, they obviously become more, pose more of a hazard, but there are many fewer of these objects. And so our mission, the DART mission, is going to be impacting a moon that's right in the middle of this, about 160 meter size asteroid. So that's something that happens something like every 25,000 years. So it's not something that's likely to happen in any of our lifetimes, but statistically over humanity's lifetime, something like that is likely to hit Earth. But that's still a relatively small scale event. On the third row here where it mentions impacts, it says that it could be deadly over a metropolitan area, but it would not be a civilization-wide kind of event. But when we start getting bigger, events that happen on the order of millions of years, we would really worry about those things. But the good news is, if you look down at the bottom, those largest things are the things that astronomers are very good at finding. They're much easier to find the big objects. And we think we've found almost all of the large and hazardous objects. And we are now working towards finding these smaller things, the things that are sort of 100 to 200 meter size, basically the size of a football stadium. That's sort of where we are now in terms of the objects that we haven't found all of yet, but still have some decent amount of risk. But we're getting very good at finding them. Another way of talking about the risk and also what this mission does is to look at this plot over here on the right, where you see different ways that we might defend against a potential impactor. And what we would employ to defend against it is also dependent on the size of the object, which is what you see on the vertical axis, but the time we have to prepare for it. So if we have something where we only have a few years to prepare, we'd be on the left-hand side of this plot, and our options are relatively limited. If we have decades of time, we have many more options that we can pursue. And so the DART mission is here. You should have just seen a dotted line show up going through the kinetic impactor region here. So the things that are kinetic are in the orange shading here. So if we have something that's say a couple of 100 meters in size and only a few years, a kinetic impactor is probably the way to go. It could potentially be useful on an object that is up to maybe 1 kilometer in size if we had 50 years of warning. And what I mean by kinetic is we're simply looking at the kinetic energy of our spacecraft crashing into the asteroid. So for those of you who have taken introductory physics, you probably remember this kinetic energy. It's 1/2 mass times velocity squared. So we have a relatively small object, in this case our spacecraft, relatively small spacecraft, but it's going quite fast. We can deliver a lot of energy. And above that would be a nuclear impactor, and that's sort of humanity's theoretical best way of potentially mitigating against a hazardous asteroid. And we are not testing that. We are testing kinetic, but the next step up above this would be a nuclear option, and hopefully that won't come to pass anytime soon. So that's some background, some motivation of why we are pursuing the DART mission and why we're interested in understanding how we might defend against an asteroid that could hit the Earth.
Dr. Knight?
Yes.
We do have a question about how likely is an asteroid strike on Earth? I'm not sure
Okay.
how large an asteroid we're talking about
Yeah,
here.
sure. So let me back up to the slide that had a bunch of words on it here. So we see on the second row here, it says frequency. And so the frequencies are telling you about how often something of a particular size hits us. So the size of, so the second column here at 25 meters is something that happens about once a century. That's an event like the Chelyabinsk one over Russia in 2013. The last one of that size was also, by coincidence, over Russia in around 1900 called Tunguska. So that sort of thing is probably the biggest that's likely to happen on any of our lifetimes. But then if we go on timescales of tens of thousands or millions of years, then we do need to worry about larger objects. So hopefully that clears it up. But if you want more, then feel free to type away in the chat and Kathy can ask me further questions. All right, so I was getting into to talking about what the mission is actually going to be doing. So the mission has 4 level 1 requirements. These are the top level requirements that NASA has tasked the DART mission with. The first one is probably the most obvious. It is to impact Dimorphos. So if the mission does not manage to hit the asteroid, then of course it's a failure. It does not achieve what we're looking to do. We're pretty confident that's going to happen. But then after that, we get into the things that we don't really know what will happen. We've got educated guesses, but that's where we're really going to be doing our science. And the second and third ones are the two that I'm heavily involved with. So the second requirement here is that we're going to change this orbital period. So change how long it takes the moon to go around the main asteroid by at least 73 seconds. And 73 seconds might seem like an arbitrary amount, but it is about 1% of the current period. So we want to be able to change that period by about 10%, or 1%. And then for the third point, we want to be able to know that it was changed with an accuracy of 7.3 seconds. So in other words, if we change the period by, let's say, 90 seconds, we want to make sure that we know that that number is 90 plus or minus 7 seconds. So it's within, say, 83, could be 83, could be up to 97, but somewhere in there, we know it very well. And those are the two things that I'm going to be involved with, and I'll speak more about those in the next few slides. And then the last part is to measure something that we call beta, which is just a parameter which will characterize the impact and help us understand what the composition and the structure of the asteroid that we hit was in that region. And that's going to be very important for planning future missions if we did have to mitigate something. And I'll talk more about that near the end. So before I get into talking about the science, I did want to just throw a few pictures out there for you to see, to get a sense of really what the spacecraft looks like and the size we're talking about. So this is the spacecraft, the DART spacecraft. Shortly before launch, it was in October of last year at Vandenberg Space Force Base. And it was actually constructed in Maryland at Johns Hopkins Applied Physics Lab, and the team got to go out and see it last August. So I have a picture of myself with it. And it's about the size of a large refrigerator, maybe a small car, as you can see here. It weighs around 1,200 pounds, 550 kilograms or so. And it launched on a SpaceX Falcon 9 rocket. So a couple of other pictures here with another person for scale, and then actually on the launch pad in November, just before Thanksgiving. And then one other picture during the launch. I did not get to see the launch, unfortunately. I was here in Maryland and missed it. But I was able to image it from a telescope at the Naval Academy. So I don't know if this picture will show up particularly well, but if you see two dots that are moving sort of near the middle from the lower right towards the upper left. And we took this picture about 12 hours after it had launched. What we're seeing here, the leading bright dot, is the DART spacecraft itself. And the thing that's getting brighter and fainter and brighter and fainter is actually the booster rocket that was tumbling. And we were seeing the wide side of it and the narrow side of it just in consecutive frames. So this was my way of getting to see the DART launch, was to get some pictures of it from our telescope right at the Naval Academy. So this next video, again, I apologize if it doesn't come through that well, but this animation was put together by the mission. And I should say almost every slide in here was put together by the mission, by people at Johns Hopkins. So they're really great quality graphics that I would have never gotten to put together myself. But this shows us the timeline of things and gives you a schematic. So you can see the spacecraft never gets particularly far from Earth. And as we get to later this year, really what happens is that DART gets in the way of Dimorphos. So it's not so much that we're hitting it by speeding up and crashing into it, as we're more like a bug on the windshield as your car drives down the highway and crashes into the bug. So the spacecraft just gets in the way of the mission, of the asteroid. This is another view of it, which I will let this play, and I'll just keep talking over it. The impact itself will be at a speed of about 6 kilometers a second, so something like 4 miles per second, which is obviously quite fast for us on Earth, but in terms of astronomical terms, it's reasonably slow. This is a cartoon. We don't really know what the system looks like at all. We just know that there's a main asteroid and a smaller moon that's going around it. And so, as you just saw, the spacecraft will crash into it, and now it will change the orbital period. And so our expectation is that the moon will now orbit in a slightly smaller orbit. It'll take, it'll change how long it takes to go around, so a slightly shorter orbital period, which we will be able to detect from Earth.
Dr. Knight, I
Yes.
have another question.
Sure.
Which is, how did you decide how much the spacecraft should weigh?
That's a great question. So this is all dictated by how expensive, so to speak, the mission is, how much fuel we can carry, how much the excess mass that the launch vehicle can provide. And so we were very tightly constrained. I don't recall exactly what the total mass allotment was. I want to say it was maybe 700 kilograms, 800 kilograms. It was under 1,000 kilograms, so under about a ton, including all the propellant that the spacecraft was going to have to get it from Earth to the asteroid. And so we tried to build the DART spacecraft as light as we can while still accomplishing the science goals that we want. But we also did want as much mass as we could have, because the more mass we're carrying, then the more energy that we're providing. But again, it's really limited by how much the rocket the payload could support. Excellent question. All right, so back to the slide here. So this is just a still frame version of the animation I was just showing. So showing you the impact, the change in the orbit. The one other piece I haven't talked about yet is this thing called Licia Cube. So the DART spacecraft, the primary spacecraft, you see that has the wings, and that's going to be the thing that actually deliberately impacts the asteroid. And DART will take pictures up until the very last moment. We're hoping to get pictures from within the last second or two, just prior to impact. So we'll see close up what that surface that we hit looks like. But obviously, once it crashes into the asteroid, we won't have any more video or pictures from DART itself. So DART also carries this very small CubeSat called Licia Cube, which is being provided by the Italian Space Agency. And that will be deployed or separated from the primary spacecraft, DART, about a day before. And Licia Cube is going to fly by at a safe distance and take pictures, a very limited number of pictures, and then transmit them back to Earth. So we will get a few snapshots from very close in of what happens, but it won't be a real-time feed, and it won't be a long-term thing. Licia Cube will just fly by, and that'll be that. So the vast majority of what we're going to know about this is going to come from our subsequent observations from the Earth to characterize the system. And again, that's where I'm involved, so that's what I'll be talking about on the next few slides.
And before you get into that, we've got a couple of questions about that.
Sure.
One was about the speed. We talked about the weight, but we talked about the speed and the mass. And we have a question: why not make it go faster so that you get more impact energy?
Yeah, so I was not involved in all of these deliberations, so I'm going off of a rough knowledge of probably what was happening in the discussions, but I think it was a cost thing. So how much was the mission budgeted for? And the faster you go meant you were launching with the bigger rocket, and the more expensive it is. And the vast majority of the cost for this mission is in the launch itself. This was by NASA standard, this was a quite cheap and fast mission. But I think the bigger point too, though, is just simply that when the mission was proposed, when it was just an idea, we looked at the energetics of the system and said, this is about the level of energy we need to do the experiment the way we want to do it. You risk, if you deliver too much energy, you risk blowing up the moon, which actually doesn't help us for our purposes. What we want to do is to understand how much energy we delivered and how that changed the asteroid. And if you destroy the asteroid, then you don't have a great measurement of how you changed it. So we want to be able to move it by a relatively predictable amount, which we can then easily follow up.
And that really ties into another question, which is it possible that Dimorphos would be disrupted itself, which I assume means, is it possible we could actually blow up that asteroid?
It is. We have a whole host of simulations. This has been done. Several different groups around the world have run their simulations of what they think will happen. And there's so many unknowns, which is part of the motivation for doing this, that we really don't know exactly what will happen. And so in the realm of what are the possible scenarios, full disruption is there. It's considered a low probability event, but it is not ruled out. But this is, again, why we're making an investigation like this, because when it matters, if the Earth is in jeopardy of being hit by something, we want to make sure we understand likely what that object is made out of, or the way its internal structure will be affected by whatever means of mitigation we're going to try and use. And so we're getting this first data point now with doing it so that we get that feedback in the future.
And so we have one more question that sort of ties in with that, which is, will changing the orbit of Dimorphos also change the orbit of Didymos around the sun? Will it affect Didymos as well?
That's a great question. By a very small amount, but yes. And so the reason, in fact, that gets into, that's a subtle question. It gets into why we're doing this on a moon instead of an asteroid itself. And so we could just impact Didymos proper, if anything, or we could impact an asteroid of the same size that doesn't have a moon there. And we would shift the whole system by the same amount that we're shifting by hitting the moon. The difference, though, would be it'd be very difficult from Earth to tell how much we've shifted it if we were only moving the main asteroid. And the reason for that is that the amount we'll move the main asteroid isn't very much at all. It's probably, in my ballpark calculations, I haven't talked to anybody in the team on this, but my ballpark calculation is we'll only shift it by a meter or something less than a meter. It's the total change that we're really measuring in terms of a velocity change, and it's like a centimeter per second or something effect on its speed. But that small shift or that small change is difficult to detect from the Earth, certainly at the accuracy that we want. However, if we shift the moon and slow it down by 1%, what we can measure very precisely is how long it takes to go around the moon, or to go around the main asteroid. And so that's the genius of DART, is by hitting the moon, it becomes very easy to tell how much we've slowed the moon down. And then it's just simple introductory physics to calculate the difference of how much the center of mass of the whole system has shifted. So again, that's why we're going for the moon rather than the main Didymos. And I'll talk more in just a couple of slides. You'll see some real data that feed into how we determine what the moon is doing.
That's great. That's all the questions we have at the moment.
All right. These are fantastic questions, by the way. I really appreciate them. All right. So here is the cartoon version of what's happening here. So you see, and this is actually really to scale. I don't think I mentioned this earlier, the relative sizes on these things, but the moon is quite small compared to the main asteroid. So what we have from the cartoon, you can see the moon moving around, orbiting around the main asteroid. And then down below it, where you see that blue bar moving across, is a schematic of what the brightness of the combined brightness of the whole system would look like. And so what you see is that for most of the time, when we can see both the moon, the main asteroid and the moon, it's a relatively constant brightness. But every once in a while, the moon either passes in front of the asteroid, like there, or behind the asteroid. And when it does that, the total light, the combined light, drops. And it drops by a different amount, depending on the scenario. Because basically, it's an eclipse, and we're not seeing as much sunlight being reflected to us anymore. And so all we have to do is to measure to time out when those dips occur. And that tells us what the moon's period is. And that part is what I was saying we can determine very precisely. And so that's what gives us the confidence to be able to say what happened to the moon and how did that orbital period change. Now, of course, as I said, this is a cartoon of the situation. This is actually the real scenario. So this is on the right-hand side is a complicated plot that I'm not going to try and explain too much. I'll point out a few things. And then on the left is some actual data that the team got of the Didymos system itself. And so if you look at that picture on the left, you may see a little white dot that's moving sort of from left to right and diagonally up gradually as the animation goes. And that is what we see here from Earth. So all we're seeing is a point of light. And what astronomers do is we measure that point of light very carefully, and we can see subtle, very small, subtle changes over time. And those subtle changes are on the top plot here, which look like a mess. And it's only when you get enough data that you can start to do some fitting to it and realize, and this was not, I was involved in collecting the data, but Kravitz, who's listed there in the bottom left-hand corner, is the lead author on doing this. He's been studying the system for about 20 years. So he's the one who has his own techniques for being able to separate out and figure out what is the signal from the main object, that primary asteroid. And if you can subtract that out, that's down on the bottommost curve, subtract that out from the whole data, then what's left over is the signal from the moon. And so you can see on this plot in the middle there that there's a dip at around 0.3. And that dip is one of those times for an eclipse. And there's another dip at around 0.7, which those help us learn the timing. Now, they don't look like much, and I want to emphasize this was actually an extremely challenging observation to do. If anybody is familiar with professional telescopes, we were using some of the absolute top telescopes in the world, and they're listed in the bottom right-hand corner there. Gemini and Keck are two of the biggest, most powerful telescopes we have. And this was right at the limit of what they could do, because what we need is extremely high precision, because the amplitude, the difference between peak brightness and minimum brightness is quite small in this case. And we did this a number of times over many years. So you see, if you look at the dates, this first slide was from January of last year. The second slide was from March of 2019. I believe I took all of the data on this slide, although I can't remember off the top of my head for sure. But this was, the shape looks a bit different of the overall, what we call a light curve. So the brightness versus time was a bit different this time versus in 2021. And that's interesting for us as well, because that's happening because we're viewing the asteroid from different angles. As we're orbiting the sun, it's orbiting the sun. When we look at it from different sides, we see a slightly different cross section. So we are getting a little bit of information about what the shape of the asteroid is. But obviously, when DART gets there, and we get a few pictures from right up close, we'll know a whole lot better. But we are pulling out some subtle features of what's going on there. And I just want to mention that this campaign is a huge campaign with astronomers around the world. Here's a list of the telescopes that contributed during the 2020 and 2021 season. So that was a really key time for the mission, because that was when we pinned down exactly where the moon was going to be, so that NASA was confident that it could hit the moon when we wanted to hit it. Because our number one priority is make sure we hit the moon. And so we did that. We got the uncertainty down to exactly where we need it, using a variety of significant telescopes. And so I've got one slide here.
So Dr. Knight, there was a question about how did we first know to look for an asteroid moon?
To look for an asteroid moon, is that what you said?
Right. This system, I mean, that's not typical of a system, is it?
Well, so we've now learned that probably about 10% of asteroids have moons. It's a surprising number. And we see moons, or what we call binaries typically, all over the solar system. That's surprising. It's actually something that wasn't expected from our initial understanding of how the solar system might have formed. But now that we've seen that these binary objects, or two asteroids orbiting each other, are very common, it's telling us that that's probably, there's a common formation mechanism. And we think what's happening there, and I'm kind of getting off tangent a little bit, but is that a lot of these asteroids are rotating, and they spin so fast that the centripetal motion acceleration throws off a bit of the asteroid, and then it reforms itself into a moon. And so probably, we suspect that's probably how the moon of Didymos formed as well. And the way that we find those is by measuring the brightness of the light. And if you get a good enough data, like I was showing on those last couple of slides, you can start to model and fit and say, okay, I see a dominant period. If I remove that, what do I see after that? And then sometimes, if you're lucky, you'll see something else left over. Occasionally, we are now starting to find triple systems. And I suspect there's some quadruple systems, although I'm not confident on that. I'm sure that they're out there, even if we haven't detected them yet. So if you have good enough data and you've got people willing to really grind through the numbers, we can pull out some really impressive results and learn a lot about the solar system in the process. All right, so if there are more questions, keep jumping in, but otherwise I will mention briefly the things that I'm involved in. So I've shown a picture here of a couple of my students. We call them midshipmen at the Naval Academy, standing up in the dome of our telescope on the roof of our brand new computer science building. And so one of the things I'm very excited about is getting my students to be able to contribute to this scientific experience. And really to collect data that's usable by the mission. So our telescope is new this year. We're still working some of the kinks out. So this semester, the students have been testing it, trying to get it prepped to see if we'll be able to contribute data in the fall, around the time of the impact, that's good enough quality that we can actually use for science. So my involvement then will, besides the students, in July, I will be leading observations using a 4-meter telescope, which is a large professional telescope, not the biggest, but a fairly large one, down in Chile. I'll be doing the observing remotely, but the telescope will be down in Chile. Those are going to be exciting because they're the final observations that we as a community can take that will affect the timing of the impact itself. So if we determine that the moon isn't quite where we thought it was, we'll still have an opportunity to make small tweaks to make sure that the impact happens at the optimal time. From July and August, things will be relatively quiet from the professional telescope standpoint. We're just kind of waiting for the impact. But then in late September, all the telescopes that are able will be trained on it. In particular, I'm excited to be involved with Hubble Space Telescope observations, which will observe what we hope will be the impact and then the ejecta. So the evolution of the dust that's released by the impact. We're going to be observing that and studying how it changes over time. That'll tell us more about the impact itself. And then October and November are the key times that I'm hoping that my midshipmen will be able to contribute with observations, both from the roof of the Naval Academy with our telescope there, and then also we're hoping to get them out to Arizona on a professional telescope called Spacewatch. And then from then on until about March of next year, we, again, as a community, will be observing using progressively larger professional telescopes because the object will get, the system, the Didymos system will get fainter and fainter. And so we need bigger telescopes to get the images that we need. And I assume that at least some of the people listening are people who have their own telescopes, or at least an interest in looking at this with a telescope. So I put a slide in here to address that. Unfortunately, this is not something that's so great for us to observe from the ground, and especially not from the Washington, D.C. area. At the time of the impact on September 26th, which is shown in this plot in green, Didymos will be very far south, too far south for us to point most of our telescopes from here. And the impact will also be during daytime for us. It's going to be optimized for observations for observers who are in like South Africa and Israel are the places that'll have the best view. That's unfortunate because our best Southern Hemisphere telescopes are in Chile, and so we'd really like Chile to be able to see it. But the more important thing was for the mission to work successfully and deliver the right amount of kinetic energy, and so that dictates the time of the impact, which is just not optimal from the ground. But Didymos will be moving north relatively quickly. So by late October, it should be reasonably easy to do. And by November and December, it'll be a Northern Hemisphere object. If you're familiar with the magnitude system, there's some magnitudes that are listed on here. I'm not going to get into the details other than to note that it is not likely to be something you can observe with an eyepiece. This would be something you would need a camera on the back of your telescope to be taking pictures of it to understand, to see what's happening. All right, in the last few minutes here, I just want to briefly talk about this beta. Again, this is not something that I'm involved with, so it's the part I know the least, but I just wanted to leave you with a little bit more on what we're hoping to learn out of it. So this slide has a couple of animations just to talk about different values of this beta. So again, beta is just a parameter that astronomers use to talk about how the momentum was changed. How much energy and momentum are we delivering to the moon? And therefore, how much are we able to affect its orbital change? And this is something we don't know. We don't have a good understanding of what beta is going to be for the system. So this sort of shows three different schematics. So a small beta, beta equals 1, would result in a small change. But if beta were larger, say 2 or 4, the bigger of beta, the larger the change in the orbit. And so by taking what the observers get in terms of measuring what the new period is, then the people who model an asteroid will be able to start to learn about what happened with the ejecta. And this, again, is a nice schematic. What we astronomers actually do is going to be modeling that looks more like this. So this is sort of a typical state-of-the-art model that someone on the team has conducted of what this impact would look like in, again, a very simplified case of an asteroid. But the people who do these models will then compare their different models, shown 3 different ones shown here, and see if they can best replicate the results that we're getting from the mission. So looking at combining what the spacecraft saw as it led up to it with those few images that Alicia Cube got, as well as all the data that we're getting from Earth as we're studying the light curve. And I apologize if anybody's hearing my cats out in the hallway, but this is the fun of live streaming from home these days. All right, so wrapping up on the beta side, this is the part, again, I'm not terribly involved with, but essentially what's going to be coming out of that is giving us some feedback about what the moon was like, what was it composed, say, of small pebbles? Was it composed of larger boulders? Were there large gaps between things inside the surface that we couldn't see on approach? Things like that. And that's going to be really helpful for future missions if we did need to prevent or attempt to prevent an asteroid from hitting the Earth. So I just want to wrap up by mentioning that this isn't the end. DART is not the end of studying the Didymos system. There's a companion mission which is being planned by the European Space Agency. It's called Hera. And the plan is that it will launch in the next, I forget which year, I think maybe next year. But it's going to be going to Didymos. It's going to rendezvous and it will orbit Didymos for an extended period of time. And as it's orbiting, it will just be taking pictures, collecting data, and learn everything they can about the asteroid after the impact. So we hope there'll be a crater. They can study it. They can look at how did ejecta fall on it, the surface. They can very carefully measure the mass and things like that. So combined with what we know from DART, with that detailed picture that Hera is going to get, we'll really have a fantastic understanding of this asteroid, which will be extremely valuable, again, in the future if we do have a hazardous asteroid that might hit Earth. So I will wrap up here. I just wanted to give you various ways you can engage with the DART mission if you're interested on social media. We have a large presence. I expect you'll see quite a bit more in the lead up in late September. And I hope if you're interested, you will follow along. So thank you very much for watching.
Thank you, Dr. Knight. I don't have any more questions right at the moment from the audience, but I do have a couple of other questions that came up during the process of your talk. You talk about Earth being impacted by asteroids of various sizes at various frequencies. Is any part of Earth more likely to get hit by an asteroid than any other part?
Yeah, that's a good question. Well, so the easy out would be the parts that have water are more likely because there's more water. I mean, roughly 75% of the Earth is covered in water. So the parts that are wet are more likely to get hit. But I think what you're really asking is Russia statistically more likely than other places? And the answer is for the most part, no. At any given time, the side that is headed towards that that's in our leading direction as the Earth rotates, that's leading us is generally more likely to get hit. But of course, that changes over 24 hours. So it's not like there's one particular part that's necessarily more likely. I suspect that the poles are probably less likely than things near the equator. But other than that, I think in any given longitude is roughly equally likely, I suspect.
Great. We do have one other question where somebody's asking to tell us a little bit more about the Didymos system generally. Do we know anything more about that system and its makeup and how it travels?
So we've characterized it to the best extent we can. I suspect it's probably the best studied binary asteroid that we know of, because this mission is happening, but also just it has an orbit that has been easy for us to observe well from Earth. Although largely this is because we have a mission going there, and so every big telescope's been willing to look at it. So we know the orbital period very, very well. It's just under 12 hours, and we know that to like a thousandth of an hour, I think, is the uncertainty in the orbital period now. So basically, we know it within a couple of seconds. Actually, it's probably even smaller than that. We have a pretty good idea of the mass, and the mass, I'm not going to get into how we do that, but we can really only learn masses of asteroids if they're binary. But so by knowing the binary system, we've got a pretty good estimate on the mass. We'll know that better after DART, but especially after the Hera mission. We know we have an idea of what the shape of the primary is, because as I was mentioning on those real light curves that we've collected, when we view it from different sides, we can start to piece together what its shape is. Those sorts of models are never definitive, and they generally can't, they're not sensitive to if there's a hole or a sort of a dip in it. So things that are concave, we don't see those very easily, but we do have a sense of what the overall bulk shape should be. We're hoping that we might be able to infer what the shape of the moon is, although at the moment we don't know that yet. The mission will determine it, but we're hoping we can do it from Earth between now and September. Surprisingly, we don't actually know how fast the moon is spinning. So we know that the main asteroid rotates in around 2.2 hours. We know the moon goes around in 12 hours. We are assuming that the moon is actually tidally locked to that orbital period. So probably the moon rotates in 12 hours as it goes around, which is the same as our moon with the Earth.
Right. Can you explain tidally locked really quickly?
Yeah, sure. So what that means is that the same face of the moon would be facing the asteroid all the time, like the Earth's moon. So for us, the dark side of the moon, so to speak, is always pointing away from the Earth. So we here on Earth never see the far side of the moon because it is tidally locked. So we always see the same part. And we suspect that's the case with Didymos, the Didymos Dimorphos system. But we don't yet have good enough data to figure it out for sure. Again, we're hoping to figure that out from Earth in the lead up to it. It just requires extraordinarily good data. And if we don't figure it out, then DART and Hera will figure that part out too.
So it sounds like you're figuring out a lot of data in terms of mass and everything. You don't necessarily know what the composition is, however, correct? And part of what you're doing is kind of figuring that out by how much your beta response is.
Right. I mean, that's factoring in. We do have some sense, and I didn't think to mention that, but we get spectra. So by doing spectroscopy, we spread out the light over different wavelengths. And we've studied enough asteroids and then the meteors that make it down to the Earth's surface and compared the two to have a sense of if we see a particular type of spectrum with a particular shape, we have a pretty good idea of what that means in terms of what it's made out of, its bulk composition. So from that sense, we know what the rough bulk composition is, but at a granular level, if you get up close, no, we don't know what that necessarily looks like. And that's where the beta can be useful, but it also can be affected by just local topography, which we will only know from the imaging. And what I mean by that is that let's say that the Didymos or Dimorphos, the moon, it's mostly covered in small rocks, say things that are pebble size up to smaller, maybe foot or two size boulders. But if there happens to be a single 10-meter or 10-foot size rock somewhere, and we happen to plow directly into that rather than all the little gravelly things around it, we'd get a very different reaction. And so we'll never be sensitive at that level here from Earth, but the spacecraft in those last few frames, as it gets close, will be able to see that and give us information about that as well.
So it sounds like, the change you're hoping for a big enough change to see the change,
Mm-hmm.
and a small enough change that you don't destroy the moon. How in realistically down the road, obviously this is very early testing, how how big a rocket would you need to actually be able to move a larger asteroid deflected enough that it would not actually strike the Earth?
Yeah, so that's a great question, and that's not my area of expertise. So I'm just going to be speculating here. But I will say that the speeds that we achieve with rockets are low compared to the speeds that these objects just have in it intrinsically. So even like the mission that we sent to New Horizons that visited Pluto, I believe was not going substantially faster enough to make a huge difference than just what sort of the orbital velocity would be as one of these things comes near Earth. So we could speed ourselves up a good bit, but there's the rock itself is already going to have a lot of speed. But where we can improve that is if we hit it head on, rather than catching or getting run over by this. So in our case, we're kind of leading it and it comes in behind us and crashes into us. And so we might be going 25 meters per second and it's going 30 meters per second, or kilometers, excuse me. So that gives us our difference of velocity. But on the other hand, if we hit it head on, if we're coming 25 one way and it's coming 30 the other way, now we can have a velocity of 55 meters per second, kilometers per second. I keep talking on Earth-based terms. 55 kilometers per second. So that sort of thing would be able to really ramp up the speed differential and give us a more energetic result that way.
Okay, well, that's what I have right now. I was going to ask you about amateurs if they could do anything data-wise to help out on the project, but it sounds like you need it's a fairly small system, and you would need a pretty big telescope to be able to collect any data that would be
Yeah, well, I
helpful.
mean, so it's interesting. At the closest approach to Earth, right around the time of the impact, it's quite bright. In fact, part of the problem on the professional telescopes is it's too bright. It saturates too quickly. So from that standpoint, amateurs can contribute. The problem is that we also need this really good sensitivity to the measurements, and that's where it takes a very stable system, observation system, and we need continuous data over something like 6 hours at a minimum. So it's a tough commitment for people to be able to do it that well. It's also complicated by the fact that it's moving through the Milky Way. So you're just going to have stars everywhere in your field of view. And so one thing that you need is a system with a very good optics, very good observation environment. So observing from here in the DC area with light pollution and whatnot, you just can't get great seeing. If you happen to be an amateur who has access to a mountain out in the desert somewhere, you might get great seeing and could be able to get good enough data that would help us. So I don't want to discourage people. And if you go browsing around these websites, if you think you've got what it takes to be able to contribute, go browsing around these places, and you should find some links to see if you might be able to contribute. Or you can look me up and get in touch with me about this as well.
We do have one more question, which may be a little bit outside of your area of expertise, but someone wants to know, does NASA have a design for the nuclear option?
That is definitely beyond my expertise, and I believe the answer is no. But again, that's just not something that I know much about. Other than that, it's been very clear that from the pure research side that we're not developing nuclear capabilities. So I can't speculate further than that.
Going back to a less violent means of deflecting asteroids. We have an interesting question here. I heard about the technique of merely placing an object near a threatening asteroid, and the gravity will alter the course and steer it away from Earth. How big would it have to be, and how far would you have to do that in advance?
Yeah, so that is a great question. And let me see if that slide has that on there. And I was actually thinking that there's some fun things that I could mention for that if people asked about it. So we're on this slide. Yeah, so it's over there on the right-hand side.
All
Where
right,
it
hang
says
on a
tractor.
second. I'm going to need to put you back in. There's the
Oh.
slide is back up.
Okay. So on the right-hand side, it says tractor in green. And that's the gravity tractor option that question was about. I've never looked into what the math is in terms of what the mass you need or the distance that you need, but I don't think that it's that exorbitant. The thing you really need is time. So you see the tractor option only becomes available if you've got decades, so 20, 30, 50-year kinds of things. If you have even longer than that, you can go further. And for those of you who aren't as familiar with it, what that's doing is literally just if we move something that has a good bit of mass close to an asteroid, and then that new mass now is going to cause a very slight tug on the asteroid, even if it's just millimeters per hour or something like that. If you have a long enough time, that's going to slowly pull it away and give it some acceleration. And you don't have to move it by a whole lot. So the Earth orbits the sun at a speed of about 30 kilometers per second. So if you think about it in that aspect, if you slowed Earth down, or if you slowed the asteroid down by 10 seconds, in 10 seconds, the Earth moves 300 kilometers. So Earth is only about 6,000 kilometers across. So you can, or is that? That's 12,000 kilometers across, 6,000 kilometers in radius. So if you just slow it down by a minute or something like that, and you've got 50 years to do it, you can cause the asteroid to no longer be on target to hit the Earth. So that's the way we would employ something like the gravity tractor. I'll just mention another one of my favorite ideas for how we might potentially prevent an asteroid impact would be to go out and paint half the asteroid a different color. So asteroids are generally speaking quite dark, and if we painted it, say, with bright white light in the right way, bright white paint, that side would reflect more light than it currently absorbs. And that would, over a long period of time, what's called radiation pressure, but the pressure of sunlight hitting the side of it, and then also the re-radiation of the absorbed energy at infrared wavelengths, if done in the right way, just painting it would be enough potentially to cause it to not hit the Earth.
Wow, so we could just paint the asteroid
In
out of the
theory, yes.
path. Well, that's pretty cool. Do we have any more questions for Dr. Knight? We've had a lot of questions tonight. I'll give folks just a second. Are there any other any other references that you would like to send people to, or anything that we should be looking for regarding the mission? You say it is September 26th, right?
Correct. Yeah, and I imagine in the weeks leading up to it, you'll see it all over the news and social media. I'm sure, and they've got a Twitter presence already. I'm sure you'll be seeing it on Twitter. So follow it there. Keep an eye out. Hopefully, you'll see stuff in the post about it too.
Hopefully so. Somebody does ask, how would we apply the paint to the asteroid?
Yeah, that's a tricky problem, and that is definitely not my area of expertise. I'll leave that to someone else.
Okay, well, I would like to thank you, Dr. Knight, for giving us a lot to think about tonight. I also want to remind everybody that this is brought to you by the Friends of the Planetarium, Arlington's David M. Brown Planetarium. We hope that you will tune in for future programs. We will continue to do things virtually, and we are going back to doing some in-person events as well. We hope to be bringing you something about the total lunar eclipse coming up very shortly. And we will also be partnering with NASA as a community event this summer, talking about the first light, the first images coming from the James Webb Space Telescope. So we have a lot coming up, and we're working to try to get the planetarium back open after its construction closure. But we need folks to contact the school board and remind them that we want that planetarium open because they're delaying it a little bit right now. We hope that you will come back and visit us soon. Go to our website, friendsoftheplanetarium.org, and check in for future events and for what's happening at the planetarium. And we will see you soon. Thank you very much, Dr. Knight.
My pleasure. Thanks for having me.